Hello! The content of the following talk, Forming New Bonds, Ditopic Organoboranes in Reduction Reactions, was presented at the 251st ACS National Meeting and Exposition in San Diego, California. My name is Thomas Käse, and I am a PhD student in the group of Professor Dr. Matthias Wagner at the Goethe University in Frankfurt, Germany. What is special about boron? Neutral tricoordinate boron atoms are isostructural and isoelectronic to carbocations. With their empty p orbitals, they are able to mediate pi electron density delocalization between adjacent pi systems. Boron doping into polycyclic aromatic hydrocarbons can therefore influence the optoelectronic properties, resulting, for example, in strong photoluminescence and improved charge carrier uptake. Regarding charge carrier uptake, it is essential to know what happens upon injection of an electron into boron-doped polycyclic aromatic hydrocarbons. So far, there is little known, but in principle there are two cases. First, the unpaired electron can be localized at the boron atom. Having two boron atoms in close proximity, this might lead to the formation of a boron-boron bond. Second, the odd electron can be delocalized over the entire extended pi system. In the following slide, the synthesis of the investigated organoboranes will be shown. Starting from 9-bromoborafluorine, triethylsilane was used to furnish the native unsymmetrical form of 9H9-borafluorine via bromine-hydrogen exchange. This dimer can be used in a hydroboration reaction with tert-butyl acetylene to generate a diboral methane, as seen on the left, or, upon elevated temperatures, a rearrangement reaction takes place, though that the symmetric diborane 6 derivative on the right is obtained. In both molecules, the diboral methane and the diborane 6 derivative, the boron atoms are in close proximity. In the diboral methane, the pz orbitals are empty and electrochemical reduction happens reversibly at low to medium cathodic potentials versus ferrocene-ferrocenium. In contrast, in the diborane 6 derivative, the pz orbitals are involved in BHB 2-electron 3-center bonds. Without a low-lying unoccupied pz orbital, only one irreversible reduction event was recorded for the right molecule, which indicates structural changes during reduction. Starting with the diboral methane, let us now take a look at the reduction chemistry by chemical means and on a preparative scale. Using an excess of lithium metal and toluene, the neutral diboral methane was reduced to its corresponding dianion with the concomitant formation of a B-B single bond. The dianion can be oxidized to the monoanion in a comproportionation reaction with the neutral diboral methane. The monoanion possesses a rather unusual bonding situation with the B-B 1-electron 2-center bond. All three boranes were characterized with the help of X-ray crystallography. In the sequence going from the neutral borane to the monoanion to the dianion, the BB bond distance decreases from 2.5 to 1.9 angstrom, and the BCB angle over the methylene bridge becomes more acute. To prove that the additional electron density in the dianion is located amid the two boron centers, a protonation experiment was conducted leading to a BHB 2-electron 3-center bond. The same result was obtained when the neutral diboral methane was reacted with a hydride source. Also for this anion, a solid state structure was determined. In summary, the neutral diboral methane can be reduced reversibly to its mono and dianion, the first example where BB1 electron 2 center and a BB2 electron 2 center bond could be established in one ditopic borane. The electron density is largely localized between the two boron atoms, as proven by a protonation experiment. Let's continue with the diborane 6 derivative that showed one irreversible reduction event in the cyclic voltammogram. To generate tricoordinate boron atoms with empty p orbitals within the diborane 6 derivative, one would at least expect a shift of the bridging hydrogen atoms into terminal positions when electrons are injected. The resulting dianion is of interest because removal of the hydrides would furnish a polycyclic aromatic hydrocarbon with central BB bond that should have unique loose acidic and optoelectronic properties. Thus, a 2-electron reduction of the diborane 6 derivative was attempted. Using 2 equivalents of the homogeneous reducing agent lithium naphthalenide, we did not observe the targeted dianion with HBBH core. Instead, 2 dianions formed in which BB bond formation was successful as planned, but accompanied by 1,2 phenyl shifts, once in the left molecule and twice in the other. The right molecule can be regarded as a derivative of the B2H6 dianion which already Alfred Stock tried to synthesize. This is the first example of a B2H6 dianion without highly bulky substituents. For both the right and the left molecule, solid-state structures are available. When 4 equivalents of reducing agent are employed instead of 2 equivalents, the singly rearranged product becomes the dominant species. It was shown that the doubly rearranged product forms preferentially in apolar solvents and at elevated temperatures. Excess lithium metal furnishes a dianionic polycyclic aromatic hydrocarbon with a central BB double bond. The dianion is a promising molecule for coordination chemistry and furthermore a precursor to a neutral polycyclic aromatic hydrocarbon with central boron-boron single bond. With 20 equivalents of potassium graphite, the original dianion with a trans HBBH core was obtained. The nature of the alkali metal seems to play a decisive role on the reaction outcome. The heat of formation of lithium hydride exceeds that of potassium hydride by 35 kJ per mole. Lithium metal might therefore act as a hydride scavenger, while potassium is much less likely to do so. One equivalent of potassium graphite gives a monoanion as the dominant species in which a BB bond is bridged by a single hydrogen atom. The same reaction takes place when the dianion with HBBH core is reacted with an equimolar amount of the neutral diborane 6 derivative. Most likely, the dianion transfers a hydride to the neutral borane, directly leading to the BHB monoanion and a hydrogen-enriched anion that can further react to give the 2 right anions. To scrutinize if a hydride transfer is a likely reaction, the neutral borane was mixed with potassium hydride. The 2 anions to the right were the final products, which supports the hydride transfer mechanism. Molecular chemistry is based upon the directed manipulation of covalent bonds. In the systematic study presented herein, the diborane 6 derivative shown in the middle was reacted to give a variety of products. The reaction outcome could be tuned selectively by the nature of the reducing agent applied and the number of equivalents used. In all cases, boron-boron bond formation was successful. In some cases, reduction occurred without rearrangement of the original backbone. In other cases, 1,2-phenyl shifts were observed to give rearranged products. The number of hydrogen substituents can be the same as in the starting material, but there are also reactions in which hydride transfer or hydride elimination take place. I'd like to thank my supervisor, Professor Dr. Matthias Wagner, and all group members, the Fonds der Chemischen Industrie, for financial support, and you for your kind attention.